Here's an example of an optimization problem. So the example is we have a 4-liter container that must have a square base, vertical sides, and an open top. We want to find the most economical shape which minimizes the surface area of the material needed. So step 1 is we want to draw a large diagram. So we have a x distance and x distance, which we can call our length and our width. And the reason why these two are the same is because it's a square base, so the sides have to be the same. And then we have our height of our container, our box. So we need to let x equal the length and the width in centimeters. We're going to let y equal our height of our box in centimeters. Step 2 is we're going to construct a formula with a variable to be optimized. So the volume of a box is found by taking the length, the width, and the height. So we're going to multiply those three sides together. So the volume of x is the length, the width, and the height. Now we're going to multiply the x and x, giving us x squared, y, and then centimeters cubed. Now we're going to go back up to this piece of information. 4 liters is the maximum that we want inside of that box. So that is our volume. So the volume of x has to be 4 liters max. Well, we need to change that liters to its appropriate measurement. So liters and centimeters are not the same. So I'm going to give you a conversion. 1 liter is 1,000 centimeters cubed. So if we have 4 liters, that would mean we'd have 4,000 centimeters cubed. So now we can substitute that in to the equation for the volume of x. So 4,000 equals x squared y. Now we're going to create that single variable, because right now we have 2 variables. We have an x and we have a y. So in order for us to do that, we have to look back. We have this x, we have this x, and we have that y. And we need to change that to a surface area problem. So surface area is found by taking the area of a base plus the 4 areas of one side. Whoops. So again, this is the base right here. And then we have the 4 sides. which would be in the pink. So what we have to do is convert one to the other. So I'm going to solve this equation down here for y. So y equals, and I'm going to divide both sides by x squared. So I'm isolating that y. So now we can go back up. This y in respect to x is 4,000 over x squared. So now I have all three sides as the same variable x. Now we're able to use that formula right here, our surface area formula. So I'm just going to bring that down. So for our surface area, so the area of x, the area of the base is x and x. So x times x, that's the base. Plus 4x times y. So each of these sides, there's 4 of them. To get this y and x, you're multiplying each of those to give you your area. Remember that y is 4,000 over x squared. So you could change that y to the same variable. So you do 4,000 over x squared. Now we have the equation all in the same variable. I do want to simplify that second term. So the area of x equals x squared plus 16,000 over x. And we want to make sure that our area restriction has a domain of something greater than 0. I did screenshot this graph. So this is taking that function and graphing it out. So we want to make sure that x value is greater than 0. If it's less than 0, then it's going to be not existing, flat piece of paper, doesn't exist. All right, step 3 now is we want to find that first derivative of the area function. So I'm going to change that area function so that that's 16,000, and you're changing that to the x to the negative 1 power. So now we're able to find the derivative using our power rule. So we're going to bring down the 2, subtract a power, bring down the negative 1, and subtract the power. So our derivative function is 2x minus 16,000 x to the negative 2 power. Or if you want to change that power back to a positive power, it would look like this. So there is our first derivative. Now what we want to do is we want to find the x values for which the function equals 0. We're finding those critical points. So now we're going to let x, the derivative equals 0. So 0 equals 2x minus 16,000 over x squared. And what we have to do is we have to solve this for x. So how we solve this for x is we're going to move that 16,000 over x squared to the right by adding it to both sides. Then I'm going to just change that to a fraction, and I'm going to cross multiply. So I have 16,000 times 1, and then 2x times x squared. So we have 2x cubed equals 16,000. Then we're going to undo the 2. We're going to divide both sides by 2, giving us 8,000. Last step to find x is we're going to cube root 8,000. That undoes the cube. So x equals 20. So this is our critical point. Now, step 4 is to find out, using our sign diagram, if there is, in this case, a minimum. And that's what we want in this problem, a minimum. So on the bottom is 20. We don't want any numbers less than 0 because that would make it flat. And this is our derivative function. So we would test the derivative. So I'm just going to write the derivative function again. And now let's test. So when you test, you want to test something to the left of 20. So I'm going to choose the number 10. So I'm going to substitute 10 into the derivative function. And then we would substitute in our calculator. And what we get is negative 140. So that means anything in the interval greater than 0 but less than 20 would be a negative slope, a negative gradient. So it's a decreasing interval. Now let's find a number to the right of 20. So I'm going to just choose 30. So I'm going to evaluate the derivative function for 30. Then I would type it into my calculator, and I get approximately 42.2. That's a positive number. So I'm going to put a positive in that interval. So to the right of 20 and beyond is an increasing slope. So notice there is a sign change going from a negative, a negative slope. So it's decreasing, and then it changes signs to an increasing. So this tells us that we have a local minimum at x equals 20. All right, so step 5 says identify that optimal solution. The minimum material is used to make the container when x equals 20, and when we substitute in for y in the y equation, what do we get? We get 10. So what is the optimal shape? Well, this was my x, and this is my x, and that's my y. That is going to be the shape of our box that will have the minimum volume of 4,000 centimeters or 4 liters. So the most economical shape has a square base 20 centimeters by 20 centimeters and a height of 10 centimeters.